Hi, the next section, 13.3, logistic regression for proportions. So this is another type of logistic regression, essentially the same, but data look different. So when all predictors are categorical or even numeric, all predictors have just the fixed number of data points. For example, X is numeric, but it's fixed to 100 or 200 or 300. This is often the case for experiment, that we give the certain amount of calorie for all mice. Then the data may be given as a table with the following format. So this is the typical format for the data for proportion. We have basically the two variables, two predictors. Excuse me, x1 and x2. And x1 has the value n or y, and x2 is the three possible values, a, b, and c, both categorical. Then we have basically 50 observations for the first row. So 50 observations have x1 is equal to n, while x2 is equal to a. Then the number of success is here. So if x1 is n and x2 is a, then 3 out of 50 succeeded. So that proportion is 0.06. Then other cases are similar. So that we have all 6 pairs, and we have actually the different number of observations, different number of successes, then the sample proportion. So you can see when x1 is equal to y, always slightly higher the success rate. And also, if we compare x2 is equal to c seems much higher success rate than x2 is equal to a. And x2 is equal to b is in the middle. And the difference is probably larger than difference in proportion by x1 value. So basically, we want to fit the proportion or number of success on x1 and x2. So the sample size of this data set was originally the 50 plus 40 plus 30 plus 35 plus 15 plus 20. So this is the 70 plus 120. So 190 observations, but it's summarized in this table. And actually, we don't really have to have 190 observations because this table includes all necessary information. This is 200. This is actually the 120 and the 50. I think this is 190. Yeah. So yeah, basically we only have 6 lines, so we don't really have to generate the data set for 190 observations. But still, we want to account for the fact that the first line consists of 50 observations, and fifth observations only consists of only 15 observations. So we have to consider the that factor. So the first line has more information than the fifth line. So in this case, we can still use the GLM function, and the proportion is the response variable, and the x1 and x2 as the predictors. Then still we can use the binomial, the logit function. Then we specify weight. So the denominator is basically the number of observations. So the higher number of observations, then we put the higher weight on that row. Then here is the result. So x1 have 2 values. So the baseline is x1 is equal to n, and x2 is equal to a. And if x1 is equal to y, how much higher the success probability is? And that probability is actually the 0.6. 0.30. So this isn't. This does not mean the probability is 60% higher, but the coefficient of x1 of the indicator variable of x1 is equal to y is 0.6. Then we have complicated the link function, inverse link function f inverse. So, but at least we can say that the y gives higher success probability than x. Okay. And x2 also here. So actually the x2 impact is larger. If x2 is equal to c, then the success probability is higher, and the coefficient is 2.25. So at least the impact is more than 3 times higher than the x1 is equal to y. Okay, so this case x1 and x2a is the baseline. Then if we have the information that x2 becomes c, then it has much higher success probability. If x1 is equal to y, slightly higher probability. But the interpretation of this number is a little bit harder. Actually, this affects basically the log odds ratio. So log of success probability over failure probability. So this is equal to beta naught plus beta 1 x1 plus dot dot dot. So this 0.6 means that if x1 becomes y, then this log odds ratio becomes 0.6 higher. So it's a little bit more difficult to interpret than linear regression model. Yeah, but at least we can see the significance. So x1 is equal to y is actually not significantly higher. X1 is equal to y does not give the significantly higher success probability than x1 is equal to x. And x2 value, if x2 value becomes b from a, then actually it's significantly higher success probability. And x2 is equal to c. So basically this compares b versus a and c versus a. So c, if x2 is equal to c, it's much higher probability. It has much higher probability of success than x2 is equal to a. And you can interpret with p-value. So at least we can interpret this coefficient, the sign of the coefficient, so which is better. So in this case, x1 is equal to y is better than x, x2 is b is equal better than x2 is equal to a, x2 is equal to c is better than x2 is equal to a. Yeah, and the significant, so the last two is significant. Last two are significant, and the first one is not really significant. And to be exact, what's this p-value 0.1388 means? Then that is basically the model, the testing result with this null hypothesis and this alternative. So actually, this is a kind of the leave one out, the null hypothesis. So the H1 is the full model. So to be exact, this is the mu plus alpha I is equal to n and y, but the I is equal to n is the baseline. So this is basically alpha y times indicator variable of x1 is equal to y, plus the beta A is baseline, so beta B times indicator variable of x2 is equal to b, plus the beta C times indicator variable of x2 is equal to c. So this is the case. Yeah, so this actually the epsilon isn't really the correct in this context, but the probability of y is equal to 1. So this maybe should be pi. So yeah, so this is the alternative hypothesis, and the null hypothesis is alternative less this term. So just leave one out, the hypothesis test. So the alpha alpha y is not significant. That means that if we know the information of x2, then x1 does not really matter. So that is the correct interpretation of this p-value.